record. It's going to record my annoying voice. All right. So here's a block sliding down a surface with constant acceleration. You all good?
Yes, yes.
Okay. And then, so, I don't know. I'm trying to think how to do this. So our force diagram is going to be weight down, right? Normal is like at an angle. Everybody's good there?
Yeah.
And then there's no way those two forces are going to add to give me a net force in the proper direction. So something's wrong. I need another force. What is it? Yeah. Now I suppose it would be possible for the forces to add up to a net force vector in the proper direction. Okay? I'm going to do some reference lines because in problems like these, typically you'd be given an angle, like right there. Everybody cool with that? And in problems like these, what you'll find, if you do a bunch of reference lines, you'll notice that, well, I didn't mean to do that one. You'll notice that every other angle is that same angle, right? Those are opposite angles. Normal force gets tilted the same amount of angle that the surface gets tilted from horizontal. So the surface gets tilted from horizontal. If you imagine, while that's happening, your normal force is getting tilted from vertical by the same exact amount. So that tells me that this angle here is the same, which means that angle is the same. You all good? And the most common error students make is with the angle. That's why I'm making a big deal out of it. So here's your weight going down. And then, which way does my acceleration need to be?
Down.
Yeah. Looks like the block has an acceleration this way, right? So it's not straight down acceleration. It's like down the hill, right? Parallel to the surface. So what I want then is weight down. Friction can be like this, right? And then normal force would be like that, maybe. Are you guys good with that? Do you notice that my normal force is in the same exact direction among my three representations? Do you notice this is mg, so I'm going to plug in mg for weight to make my life easier. I'm going to plug in mu kinetic times normal for friction. And in a different color, I'm going to draw my net force vector, which is the vector I get from adding these vectors. So it's not going head to tail with the rest. And that one has a magnitude of ma. Yeah. And that's based on second law. And now I really need to figure out which angle in my triangle is my right angle. Usually that's the angle between your surface and your normal, right? That's got to be 90 degrees. So I figured out that was 90 degrees. Now, if I do some reference lines, I should be able to see fairly easily that this is theta, right? That means that's theta. And I'm sure of it. But you have to be sure with your angles. Because, again, it's the most common thing people do wrong. So be methodical and be 100% certain. Have multiple ways of checking your angle. It's just too common an error. Does that make sense? It'll pay off because your whole solution falls apart if your angle's wrong. So now it really comes down to sine theta equals what? Help me. Okay, mu k. My mu sucked. Let me draw a better one. Sorry. Mu's fun to draw. Like that. Mu k. Normal. Plus ma over mg. Done. And I'll leave the algebra stuff to you. I'll just give you a general strategy here. Cosine theta is what? Normal over mg. Good. So I can solve that for normal. Normal is going to be mg cosine theta. Then I can put that in place of normal and actually solve for acceleration in terms of all the other variables. Does that make sense? That would be a classic medium level AP1 problem. Make sense? And one of the things that happens right away, you notice when I plug in for normal is m in there. See it right here? See it right here? See it right here? What's going to happen to m? This shows us something pretty interesting about how nature works. When Galileo dropped his balls, his spheres, off of Leaning Tower of Pisa, what happened? Two different masses. What happened? Same acceleration? Okay, when these spheres slid down, rolled down surfaces, that's what he really did when he was locked up, right? So when the spheres went down inclined planes at different angles, did the mass of the spheres matter then? I don't think he really dropped his balls off Leaning Tower of Pisa, just so you know. I think he just rolled balls down hills, right? That's all he really did. But my point being, did the mass matter? And look, even when you have a block sliding with friction, and there's an acceleration down the ramp, does the mass of the block even matter? It's a very deep, interesting thing about how nature works. It has to do with, if there's more mass, does the Earth pull with a bigger force? So everything's all designed so that objects have the same acceleration. It's pretty cool. Anyway, I hope you notice how the mass cancels there, and I hope you complete that problem and solve for acceleration in general for fun. Are you guys good?
Yeah. Mr. Day, are you going to post it on Evernote?
I'll put this